Okay, welcome everyone. I'm happy to introduce Noam Goldberg today. He's associate professor at the Ben Gurion University of Negev. He received his PhD in operation research at Rutgers University and later did several postdoc positions at Technion, Argonne National Lab, and Carnegie Mellon. And currently he serves as the on the editorial board of Math Programming Computations and Soft Computing. I'm very happy to have you here, Norm. Please.
Thank you very much. I'm very happy to speak here, to have this opportunity at the famous Rose Seminar, and thank you to those who showed up here. Um, I'm going to speak about robust extensible bin packing and revisiting the convex knapsack problem. And I'll soon get to how these two problems relate. This is joint work with Michael Post from Montpellier and Yariv Marmor from Ortbraud College, who helped us with a case study, actually applying the models and methods to some real data, which I hope to show at the end. So I'll briefly go over the outline, the key points, just so you know what to expect. So I'm going to start with some motivation for robust extensible bin packing and cover the literature a bit before I get to the more formal definition of the problem. And then we'll talk about how to solve the problem by scenario generation algorithm, row and column generation, and subproblem that we get as a result. And you can guess that it's going to be related now to the convex knapsack, and that's where we'll focus our theoretical part of the study and get some theoretical results as well as some computational methods out of the study. Eventually, we'll experiment with these methods for solving the subproblem as well as our original problem. And after looking at some initial experiments, we'll also look at some computational improvements, tightening the first formulation that we start with. Okay, so what is extensible bin packing? For that, I'll just briefly show classical bin packing. So in classical bin packing, we have a set of items, each one of a given size, just some scalar size. And we need to fit the items into some set of bins, the least number of bins. So in this case, we may have to fit the items into 3 bins if we need to satisfy the bin capacity constraints. And the extensible version of the problem allows us to somewhat exceed this capacity. So if we consider the extensible version, in this version, we would pack, say, the last 2 items. We managed to just fill over the top the first 2 bins. And then we may have a solution like this where we're only using 2 bins, and this would have a cost of 2 for the 2 bins, and then 0.1 C1 being the overfilling cost for the first bin, and 0.4 C2 the cost for the second bin. Okay, so depending on the overfilling cost, this may be optimal, right? But if our overfilling cost is very high, we may arrive at the special case of the classical bin packing. Okay, so some practical motivation for this problem, and for me, it's also personal motivation. So, and when you schedule elective surgeries, then you schedule them into OR shifts. And the OR shift you may have some in parallel, and you may have some over the next few days. So typically a few days or a week are scheduled in advance for elective surgeries. And we want to use the least number of shifts to schedule any given set of surgeries. So I said it's also a little personal. So my second child was actually born in a cesarean section. So I recall that day we were arrived and scheduled to have it sometime in the morning hours, but it actually took place much later that day and went into the almost night shift, being late in the afternoon. So this is to motivate the need to account for uncertainty in the problem. So when you try to schedule surgeries and your bins are actual work shifts, then uncertainty is a very important aspect of the problem. And if we schedule surgeries, we may want to use not only at the expected surgery duration, say 0.3, we may also have a deviation of that duration, 0.2 for some given surgery. And we may want to account for that. The 0.2 may be, for example, how much the surgery would take if things go wrong, if you have some complication. And if you have too much overtime and things are done late, doctors may make mistakes, and that's so the overtime cost may be quite high, not just in terms of operating, but also the mistakes that may happen when we count that as a cost of overtime. Okay, so hopefully that's a very strong motivation for accounting for the uncertainty in the problem. So extensible bin packing and the nominal form of the problem, the deterministic problem has been well studied a long time ago, starting with Del Olmo, Keller, Speranza, and Tuza in 98. And the focus there was approximation theorems and theory. And the basic form of the problem, then overtime cost would equal for all bins, and there's typically some fixed number of bins that we can use. So the objective may be slightly different, but it's a closely related problem. And there are also generalization that have a more general cost structure with possibly different costs for different bins and so on, and even more general structure than that. And the robust formulation of the problem, probably closest to the one we consider here, was studied by Denton et al. In 2010, an operations research paper. And in fact, this model that they proposed, they consider two different models to handle uncertainty, one being based on budgeted uncertainty. And in fact, it is shown later that the reformulation that they apply is actually conservative reformulation and not exact. It's shown in more recent work by Ardestani, Jafari, and Delage. And they propose some less conservative reformulations. Our approach here is to consider a closely related uncertainty set that's slightly different, which I'll show next, and we consider exact approaches for this problem. Okay, so to formally define our problem, so which is the extensible bin packing, first in the nominal form. So we're given some number of bins n and item sizes A1 through AM. And we want to find some partition of the items and to B1 to BK for some K less than the number of bins allowed, so that the total cost is minimized, and the cost being the number of bins and the overtime cost, which we can write in this form, right? So it's the overtime cost per unit time, and amount over time in each bin. And each bin J is the positive part of this amount. And the robust version, of course, where instead of given some vector A, we have this entire uncertainty set, and then we want to minimize the same objective for the worst case A in this given set. Okay, so this is the problem we're dealing with, and if you look, if you look at this figure here, perhaps when you're overfilling trucks, it may not be such a safe thing to do, but again, our motivation is more in scheduling surgeries where it's very important, and it typically happens that you go over the work shift. Okay. So the uncertainty set that we consider is the intersection of one norm ball with box uncertainty. In some places, it's known as knapsack uncertainty. And it's we denote it here by this U omega. Okay, so our here it would be the deviations are bounded by this A hat, and the sum of deviations is at most omega. So really, it's a close form to the budgeted uncertainty of Bertzimas and Sim, yet different. It's considered in some application by Gunaris, Weissman Fludis to CBRP, another paper of Poisson, as well as others. Okay, so it's also important to note that similar to standard budgeted uncertainty, there are also probabilistic bounds for this uncertainty set. And for example, you could derive one from general polyhedral uncertainty set probability bounds and this recent paper by Bertzimas and Herter Pofile. So we have probabilistic bounds also in this case. And we arrive at this set, or we continue working with this uncertainty set also from previous theoretical work on approximation, together with the standard budgeted uncertainty set. And there we had at least a feeling that this uncertainty set is easier to work with computationally, or at least we hope so, based on the fact that we got better approximation results for this set. We have some results there, both for gamma uncertainty being the standard budgeted uncertainty of Bertzimas et sim, where at most gamma items may deviate. And we have some better approximation results for this current set. And that worked for the classical bin packing problem, or a robust version of that problem. And some ongoing work, we actually have some formal results that, in some sense, this is easier to work with. But it's not a part of the current talk. I'll expand on this in the conclusion if I have time. Okay, so just some more intuition for the omega uncertainty. So let's say we have these four items. We have the given nominal sizes, and we have the deviations in red, and we have the uncertainty budget 0.3 in this case. So if we pack these all in one bin, our cost would be 1 plus C over 2 if my overtime cost per unit is C. And that would be just because the sum of nominal sizes is 1.2, and we have the additional 0.3. If we pack them in two bins, then we would not incur any overtime in any case, or our cost would be just 2 in the worst case. So what would be optimal, of course, depends on this overtime cost up to C equals to 2. We may pick 1 bin over 2. So just a bit more of a feeling here. Okay, so now we formulate this problem as a MIP. It's well, for those familiar, it's most of these constraints are rather standard bin packing model constraints, and we want to minimize first the total cost. I'll soon get to its components. First of all, we need to assign each item to a bin. That's the first constraint. The Z's are the indicator variables for assignment of item I to bin J. Of course, if a bin is used, it must be opened. And that's indicated by Yj being 1. And then we have the bin capacity constraint and the overtime cost constraint. So our overtime is theta, and that is the cost of the overtime alpha j per bin j. We have an overtime alpha j, and so the linear combination of these costs with the overtime, that's the total theta. Okay, so whatever is in excess of the bin capacity V would be the overtime. And we're minimizing the total cost, which is just the number of bins, and the overtime cost. So this is the nominal problem. And then, okay, in the robust problem, then we have in the bin capacity constraint, we have scenarios A, so we need to satisfy bin capacity, and we have in different scenarios, we have a different overtime, so that depends on the scenario. So it's basically a two-stage problem. And we have overtime cost for each scenario A in our uncertainty set. Okay, so basically it's a perfect recourse type of two-stage problem, right? So we have many such bin capacity and overtime cost constraints, and what we'd like to do is generate these. Okay, so this would be our row and column generation approach. So given some solution to the master problem, y star, z star, theta star, we want to determine a scenario so that a scenario for which these constraints are violated, right? And we can show that this amounts to solving this subproblem. Okay, so just by moving things around, we can see that this amounts to just maximizing this objective. And we can rewrite this, get rid of this overtime variable by moving things around. It's just equivalent to solving this subproblem, maximizing this objective for A's in our uncertainty set. And if we find that optimal value eta star exceeds the current theta star, then we have managed to find the violating pair of constraints. Okay, so that's the subproblem that we need to solve. Okay, so then we get to the question of how hard this problem is, and we start with given this subproblem, the separation problem. We consider first fractional solutions to the master, and we want to find whether this subproblem is hard, and we're actually able to formally show that the problem is strongly hard for given fractional solutions Z star Y star. Probably should have shown theta star here, but it's not. Well, it's less important. Okay, so the reduction is by the maximum click. So given this result, we're kind of discouraged of trying to solve the fractional separation problem, and we considered the separation problem given an integer or binary solution Z star Y star. So the question is now solving the previous objective that I showed you, given Y star and Z star that are binary, and it turns out that if they are binary, then the problem just becomes a convex knapsack problem. So just to give a hint, it becomes a separable here in the objective. So we get the objective in this form, and it's just a very, in fact, specific form of convex knapsack problem. So we have basically it's piecewise linear with a flat first segment and then general second linear segment. Okay, so this is what it looks like, just written for convenience. I don't know if I need to remind you, it looked originally like this. So we keep moving forward with the simpler form with beta and gamma. Okay, so it just becomes a problem of this form. And this is the problem we're gonna focus on, at least for the next few slides. But before
Noam,
that,
one question.
yes, of course.
Can you go back to the separation problem? One slide before. I don't understand where the hardness here comes in. For me, it looks like a classical budgeted, so maximizing over a budgeted uncertainty set of kind of a linear function.
Well, it's not linear, right? It's piecewise linear. It's piecewise linear. You're maximizing a convex function.
There's a plus there.
That's
Okay.
indeed a piecewise linear function. Yeah, sorry, maybe yeah, it's not should be made bold or something or defined. Yeah, plus
okay.
maximum of 0 and the amount in brackets. So it's a positive part of this becomes it's piecewise linear indeed, but it's a convex, and you're maximizing a convex function.
Okay, and that means in the end, your whole problem is actually a classical min-max problem with a convex, piecewise linear convex objective function, right? Without constraint uncertainty, because you can always move this part into the objective like you did in the separation problem. And then it's actually a classical min-max problem with a piecewise linear objective function, right?
If I can move into the yes, but these these variables depend on the scenario, right? So I don't know if you just mean like if we can move this around.
Yeah, but you removed them kind of, right? Because in your reformulation you don't have you have them anymore.
You're saying yeah, but I do need these in a few places, right? So this so given the z, so here z and y are fixed, right? But
Yeah, sure. But never mind. Maybe we can discuss in the end.
Okay. Okay. So all right. Okay. So continuing with our row and column generation approach before we study the subproblem. So this is the standard approach. It's a perfect recourse. In this case, we solve the master with a given subset of scenarios. And what's somewhat special here in our approach of solving the master before I get to the subproblem is the fact that we start with a loose optimality gap, and we actually tighten it later during the algorithm, and we do this to kind of computationally balance the hardness of the master problem, which is quite hard with the with our separation problem that eventually will show some pretty efficient methods for not it's a hard problem, but we're able to at least in practice solve it quite fast. So we solve the master with the loose optimality gap and tighten it once we cannot determine any scenario with that optimality gap. And once we tighten, we may find some more scenarios violating the constraints until we're finished. Okay, so we'll get to that sooner in the computational part. So now I said I would get into the convex knapsack problem. So just a brief survey of the related literature. So convex knapsack is shown to be NP-hard, at least weakly NP-hard by Levy et al. In that paper, they gave some constant approximation algorithm, but in fact, there are pseudo-polynomial time algorithms as well as approximation schemes that I'll get some more details about soon. So the first is a closely related variant suggested actually earlier. It's a minimization variant that's closely related. There was a very significant complexity for that algorithm. Okay, it's a pseudo-polynomial, but it's quite high, the complexity by Burke et al. And more recently is this result by Malaguti et al. And 2019. So Malaguti, Monarchy, Parnuzzi, and Ferci. We're not aware of this result at first, but at the end we think it's actually to our advantage that we worked on this problem because in our special case, at least, we found some improvement that we think is interesting. So these are results for general convex knapsack, which we'll also touch a bit by some alternative algorithms. And these pseudo-polynomial algorithms are also extended to approximation schemes. So once I get to our approximation scheme, I'll define it more formally just before stating our result. Okay, so just recalling our subproblem, it's of this simple form, right? We're maximizing this sum of profits, where each pj is a convex function of this specific form, with basically piecewise linear with a flat first segment and general slopes of the second segment, and subject to the uncertainty budget constraint, basically. Okay, so the previous complexity results don't apply to this special case because they actually involve a quadratic, so maximizing a convex quadratic. So first we formally established the hardness of this special case that we're interested in. So the two-piece convex knapsack problem is NP-hard. Not only that it's NP-hard, it's NP-hard with when you have equal slopes beta j. So even the special case that we many times are interested in, with over time having the same cost, whether it's on one day or the next per unit, then even then the problem is NP-hard. Okay, so now so now we consider solving a solution method for this problem, and the solution method, both our own and also others for Convex Knapsack, many times rely on this key property, stated here as an observation. Right, so in convex maximization, we know that there is an extreme point optimal solution. So there must be a solution that has, in our case, this extreme point solution corresponds to a single fractional item that's partially used, not used up to the upper bound. And all of the other items that are used are fully used. Their upper bounds are active, are tight, and then there are items that are not used. Okay, so that's one key property that's important. And another that we're able to use that comes straight from the optimality or KKT optimality, but it's quite intuitive here, so I don't state it in that form or try to derive it. It's it's fairly straightforward. So this property says that the fractional item should have a directional derivative or right-hand side derivative less than, or at most the left-hand side directional derivatives of the items that are fully used. For a solution that is optimal, that must be the case. Okay, so maybe to try to give some intuition then for this problem and this key property. So let's say we have these three items and these three profit functions. Then which items would we take? So one thing to keep in mind with this property that we know is that the second item, let's say the one that's fractionally used, will have a slope that's not as steep as the first item or first items that are used. Okay, so just taking a look at this. So I mean, it's we have a slope of 2 for the second segment, and item number 2 we have a slope of actually slightly larger than 2 for the first item, and slightly less than 2 for the third. So in this case, it may be it is optimal to take the first item and get this profit of 5, and then okay, the next item that we'll take that will be partially used will not have a slope as steep. It's one of the other two, but we can also see that what matters is the breakpoint, right? If we take the second item, we won't have we'll only get if our budget is 5, we won't get anything out of it. We'll stay with 5. And if we take the third item, we manage to get this close to 6 in terms of profit. Okay, so the combinatorial aspect also can be seen, or you can get some feeling for that through the fact that it's these breakpoints and convex maximization comes into play. Okay, so how we solve it is through dynamic programming, and the dynamic programming, unsurprisingly, will resemble binary knapsack dynamic programming. So what we do is, okay, so first I'll show I guess a more naive, or before trying to improve. So the only thing we need to take care of compared to binary knapsack is that there's some item that's excluded from the recursion. Okay, so we consider the recursion just for the fully used items, and then we need to do something for the fractional items. So we can either pick an item, right? So our zeta function is basically the weight needed to obtain a profit of P, uppercase P, and then we can either select an item, the item K, or not select it, not use it. As long as it's not the fractional item. Okay, and okay, there's some few base cases that I ignore, and we have some more base cases than the standard knapsack version. But the key difference is how we use this DP table information. Okay, so at the end, the solution of the convex knapsack is then, okay, we go over all possible profit values and all possible fractional items excluded, and then we consider the profit to be the profit P, and what we can obtain from the remaining capacity after obtaining that profit P from fully used items. Okay, and the profit we get from the fractional item is just defined by this function. It's just the profit function, and what we get if it's feasible or negative infinity. Otherwise, that's the fractional. So this naive approach, I call it, results in a complexity that's n squared p max. So it's n times the complexity of binary knapsack, and then. Now we want to try to do better than this. So to do better than this, we need to use the key properties that I mentioned. So the first one being about the directional derivatives and the fractional item derivative being at most that of the fully used ones. And another thing is to observe that in the DP, if my fractional item is it has an index. Okay, if I'm looking at a subset currently in the DP of items up to K, and my fractional items are larger than K, then of course I'm able to use the same entries in the DP table, right? So I don't need to run n times knapsack. I can reuse the same DP entries. Okay, and this observation on its own may not necessarily help, but combined with the previous observation about the derivatives does help. So the key thing is to re-index. So basically, we need to order the items by the directional derivative. So we start from highest to lowest, so that we keep the potentially fractional items, we keep it last. Basically, that's hand waving, but that's the key idea. And when we consider the lower index items, if our fractional item is back, then we can reuse the same table entries for the different fractional items that we keep in the back with the higher derivative being first, and the lower derivative ordered so that they're considered last. We're able to completely reuse the DP table entries, so we only need to compute the table entries once, basically, and then this optimization, this post optimization using the DP basically does not add to the runtime complexity. So this fact basically leads to, or is the basis for the proof of the complexity being n times p max, or to be more precise, we also need to account for the sorting, but typically p max is much larger than log n. So to be precise, it's n times p max plus log n. Okay, so that's a key result for the DP, and we also want to turn this result of a pseudo polynomial algorithm into an approximation scheme result, a fully polynomial time approximation scheme I just state the definition. For those who don't remember, is that it's an algorithm that for any epsilon, positive epsilon, we can get a solution that's at least 1 minus epsilon, the optimal value, and time this polynomial in n and 1 over epsilon. Okay, so before getting to our result, we also make this observation, or it's actually a proposition that we can reduce any binary knapsack algorithm. Okay, not by the previous algorithm that I showed. That's specific for our special case, but for convex knapsack in general, we can think of two different ways to reduce a knapsack FP-TAS algorithm to convex knapsack. So one is if we have a DP-based FP-TAS, then we can it will carry over with the complexity of n times the complexity of the knapsack FP-TAS. We can do that or show that, and that's because the DP approach would compute values for would compute an entire table, not just a single profit value. If we did not have such a DP-based FP-TAS, then all is not lost. We can have it will carry over. We can use it, but we may need some more invocations of the knapsack algorithm. So we can basically do these steps to approximate the profit values by taking some log Pmax invocations. We can have the knapsack FP-TAS carry over with this complexity of n times log Pmax times the complexity of the knapsack FP-TAS. So there are two different ways, and it's just interesting because recently there have been many developments related to approximation of knapsack, for those not aware, very recently. And there are convolution-based methods that don't necessarily use any kind of DPs, or they don't. And so if we took like the DP approach, let's say if Lawler et al., we would get this O1 squared log 1 over E plus n times epsilon to the minus 4. And if we took the second approach using the recent results, then we get actually some this complexity, and it's not really comparable. So both are interesting, I guess. Okay, so just to point out that we have these new approximation results. And these are very sophisticated methods proposed recently based on convolution. So that's just a potentially interesting observation that we also discussed, just to try to illustrate or show the relationship of a convex knapsack to binary knapsack as a part of this study. And back to the problem that we're interested in this very particular case of a convex knapsack. Again, the piecewise linear with two segments. And I should probably speed up a bit the talk. So we can expand the previous DP algorithm that I showed we can extend it to an FP-TAS by straightforward scaling and rounding. Or the standard approach, and we get this complexity that again is not strictly comparable to any of the previous results. And for our case, it's better than the previous result that I showed from the literature. Okay, so. And we also comment that if we try to go more technical and beyond scaling and rounding, many of the running time improvements of Lawler et al. Or all of them can actually be applied. It was not a major focus of our paper, but it can be actually used here to further try to speed up the algorithm, but this would be a fairly simple approximation without using the speedups by Lawler, which is quite old now, but it's a fairly technical paper and many quite technical details used to speed up the standard scaling and rounding approach. So now I get to the actual computation. And for computation, we actually put aside this approximation scheme result that I now discussed. We were actually interested in just studying the pseudo-polynomial time algorithm, the DP. Okay, so we're interested in solving this subproblem exactly. So we compare it to what we are aware of as the best practice and using state-of-the-art MIP solvers that can handle specially ordered set constraints. So especially ordered set is a standard way to handle piecewise linear functions in MIP solvers. So it allows some more custom branching to be done without necessarily declaring any integer variables. So here it just means, okay, we have this piecewise linear function, and we have basically we describe it by the breakpoints, and the t variables take convex combinations of these breakpoints. We just have three, but we need to make sure that to stay on the curve, we need to make sure that only adjacent variables of the convex combination can be non-zero. So only two adjacent ones can be non-zero, and that's exactly what specially ordered set of order 2 means. Okay, so only the two adjacent ones, TJ1 and TJ2, for example, can be non-zero, or TJ2 and TJ3, or just TJ3s, right? They need to be consecutive too. So we do this basically in Gurobi. So we define this, we formulate the model in Gurobi, and then we compare our dynamic program to the SOS model formulated in Gurobi, and you can see that even for magnitude of the parameters that is quite large, could try even larger, but we see if they're quite large, we do much better compared to the especially ordered set approach and MIP. And the magnitude of the parameters also affects the MIP. And even when we get to 100 items, we reach the time limit in solving the MIP. Here it was a short time limit of 30 minutes. And with even 500 items, where in all cases time limit is reached in Gurobi, we're able to solve the problem using the DP in at most a few minutes, very few minutes. So this is the result for our subproblem. And now, just checking how much time I have. Okay. And now we go back to our original master problem that we want to solve, and we solve an extensible bin packing problem using benchmark data from this paper by Song, Kwolczyk, and Luz. This paper that didn't look at the extensible one, but we based our experiment on their data, and we just add some overtime cost to the bins. So this is benchmark bin packing data, and here it's actually quite challenging, the extensible bin packing problem when we solve with 1%. What we look at here is we have an initial optimality gap and a final optimality gap. So tau 0 and tau 1 that we terminate with. So with 20, we can get the 1% gap, and we consider the different initial optimality gaps from 0.1 to 0.4, and we can see that it quite matters. So we can get, with the looser optimality gap, we can usually get some better results. So I'm not showing all results in this one table, but typically we get improvement with 0.4, even with 0.2. So you can see here with the final looser optimality gap that we do have most of the times we have improvement with starting with the looser optimality gap. And okay, so but we see these instances are quite challenging, right? So I'm at the end. I'm gonna show some more, just making sure that I have enough time. So we're gonna look soon at computational improvements that we apply to the master problem as well. I should also comment that here we start with a given set of bins that's some very high upper bound. So we can start. So we're allowed to use many bins, and it's a part of the objective to use the least cost set of bins with possible overtime. Many times in surgery data, then you actually have some fixed set, or just because of procedure, you now try to determine a schedule for the next week. Many times it's a week, so it's just 5 days, 5 bins, or let's say 10 if you have 2 operating rooms that to schedule the same types of surgeries. So now I'm gonna look at our case study before getting to the computational improvement that I promised. So I'll quickly go through that. So we applied this model to some real surgery data made available by the Service Engineering Lab in the Technion, and we estimate the surgery types not by some given medical categories, but this is actually there's some data-driven component of this work. So types is actually something we need to determine. So the problem, you can think of the real problem as driven by data actually. So we can predict surgery times based on different diagnoses and different information of each patient. It's not only like a medical category. So we consider 2 different regression trees as a way to estimate the nominal and deviation surgery durations. Okay, so at each leaf here, we basically have some expected surgery time, and we have, in fact, a whole distribution which we can use to estimate the deviation. So we have a small regression tree, and we have a quite larger regression tree that gives some more predictive accuracy, not much more, but in this area, that's probably as high as that's you can get a bit higher than this, but not so much more. So you get a more complicated tree, but somewhat more accuracy. So that's just I emphasize that because I think it's important in terms of running our model. So now we compare in our robust experiments versus solving the nominal model and the actual scheduling that took place. So for the scheduling, there's no difference between the regression trees, V1 and V2. And we look at the overtime, which is most important or most interesting for us, as well as utilization. We actually see that the robust model improves both in terms of the overtime and utilization. Of course, compared to the actual, both the robust and nominal improved. But we improve here compared to the nominal. And what I find interesting is actually that the robust is able to improve making use of the more complex tree. So the complex tree has, in this case, we can see does not necessarily give any improvement for the nominal model, but the robust model is able to exploit the more accurate complex tree. And this you can attribute maybe to what's in machine learning terminology is referred to as a kind of overfitting, maybe. So the robust model is able to exploit the more precise tree that's highly complex. So it's also robust to the estimation error, you can say, of the surgery duration, it seems. So I have to be a bit careful in stating that, but yes, that's what it seems. So just before, so we don't have so much time, so I try to speed this up. So I promised some improvement. So to get some improvement, this is fairly quick. We exploited well-known symmetry breaking inequalities. So we ordered the bins so that a bin is opened only if the preceding bin is open. So J plus 1 can be opened only if the previous one is open. And having these symmetry breaking inequalities, we can also propose a new inequality that relates to the overtime cost and the uncertainty aspect of the problem. So we can say that the overtime cost has to be at least, okay, if a bin J plus 1 is not used, meaning we use at most J bins, then the overtime has to be at least the sum of the nominal times, the plus omega, the total deviations, minus the J bins. Okay, that's whenever we know that at most J bins are used. So we add these inequalities, okay, of course, multiplied by the per unit overtime cost. So these inequalities are valid for every integer solution must satisfy them. So when we consider these in our computational experiments, and now you can see that the results are much better, especially if you look at the final the ones that we solve closer to optimality with 1%, and you see in terms of the time limit being reached, much fewer cases it takes place. And we see improvements also in bigger instances where we don't necessarily solve to optimality, but even with 90 surgeries that we're scheduling, you can see a significant improvement also in terms of the time limits and the elapsed time when time limit is not reached. So both the symmetry breaking inequalities and when combined with our valid inequality, we see quite an improvement. So I think we're really at the end in terms of time, but the conclusion is just to summarize. Then we focused on theoretical aspects as well as computational for the subproblem. We have some approximation and complexity result for this specific special case of convex knapsack. And we have a dynamic program that's as fast as a binary knapsack using some structural properties of the problem. We were able to show that, and we get improvements in practice using this DP compared to state-of-the-art MIPS. And we have future work both that we're considering is both computational, and we have a parallel theoretical investigation of robust extensible bin packing that we're interested in and is ongoing, but we have some results there, like I said, about the formal aspects of the complexity of our version of budgeted omega uncertainty versus the original gamma budgeted uncertainty, and there's some key differences in terms of the complexity of the problem. And we can show that in this ongoing work that there is actually an asymptotic approximation scheme as opposed to omega uncertainty, gamma uncertainty, where in previous work we showed that no such scheme can exist. So that's a theory work that's related but ongoing. Sorry. So I think I conclude here.